So it's a great pleasure to be here to present the works I've been doing in the last years with my colleagues. So this is work that has been done with colleagues from the University of Trento and some people also at Snapchat. Thanks for them for all the work we did together. But before talking about video generation, I just wanted to give a quick overview of the research I do. So I work on computer vision and deep learning. I'm focusing on, let's say, three main topics. First one is, let's say, traditional perception problems, like pose estimation, depth estimation, segmentation. But now my main two interests are domain adaptation and image and video generation. So today I'm going to focus only on this problem, but if you are interested, we can maybe get in touch to discuss other topics. So in the last years, we have seen great progress for generating images and videos. Most approaches are based on a very similar principle. That is that we try to learn a mapping, a network that maps a known distribution, such as a Gaussian distribution, to the distribution of the data that we want to generate. So in this way, at this time, if we want to generate new data, we can just sample according to this prior and use our mapping to get realistic samples. And so this can be applied for images, but also for videos. But when it comes to videos, usually it has severe limitations. It requires a large amount of training data, and the training is really costly. And usually it does not offer much control on the generation process. So in the sense that if you just use this unconditional generation model, you're going to get some images, but you don't really control what you get. So in the field, we try to design many ways to add control and to reduce the amount of training time. And my research is going in this direction. So in the last years, I've developed three main ways to provide to the user some interactivity on the content. So I want to quickly mention these three works. The first one is a new task that is do as I do, where basically you can control the generation by providing the motion from another video. The second task is a do as I say, where basically you can say action, you can tell actions to the network in order to control what's happening in the video. And finally, a last task that is the go where I click, where basically we can control the motion of the object in the videos by clicking on some object of interest and pointing where we want this object to move. So in this presentation, we're going to focus only on the first two problems for sake of time. But in general, over these three problems, what we try to do is to address these problems while using as little supervision as possible. So you will see that in all the methods that I will detail, we don't want to rely on heavy annotation or heavy prior that we have on the specific object that we want to animate. Okay, so let's focus first on the do as I do task. So in the do as I do task, we receive an input, a driving video, and a source image where the object category of this driving video and the source images are the same. And the goal is to obtain a video with the appearance of the source image, but the motion of the driving video. And so several works try to address this problem. And they were using, let's say, a naive solution that is just using image-to-image translation. So in what we can do to apply image-to-image translation is that we can detect the pose in every frame of the driving video. And then we can train a network to go from the combination of the source image and the pose to get an image with the pose corresponding to the one estimated in the driving video, and with an appearance corresponding to the source image. So more in details, what we can do is that we can collect a long video of someone moving in all possible body pose. So we use a body pose extractor P, and we get a large data set of skeletons. And then we can train a generator network that will map this skeleton to the RGB image that were recorded initially. And then at this time, what we can do is to take a new video, detect the pose, apply some normalization to handle the difference of body proportion between the training data and the one we receive at this time. And then we can just reuse the generator network G to map the skeleton to the RGB images. Okay, so it's very straightforward way to use the pix-to-pix algorithm in the case of human pose. But this approach where we proceed in this way has several limitations. First, it can mold a single person. So in the sense that you need to record 20 minutes of this person moving to get a model. So you need a long time to train this model. And this model will work only on this person. Then we can imagine that we can have a more complete training where we have big data set with many people in order to be able to combine the pose and the appearance in the image. But it still suffers from a second problem. That is, it requires a detector or a pose estimator. So it works really well if you are dealing with humans, like we have pose detectors that are publicly available. But now if you are working with robotic data, like this bare data set where you have a robotic arm grasping object, you don't have a key point detector available for this kind of data. Or if you are working with cartoons, here you won't get neither a detector, so you will need first to annotate some key points, train your detector, and only after that you would be able to train your model to animate the images. Okay, so in this first work we try to handle these two limitations in order to come with a model that can animate any new image of a specific object category without requiring any prior information such as detector or key point estimator. And so what is the solution that we proposed is it's a self-supervised motion transfer framework. So what we try to do is to learn a motion representation that we can transfer from one video in order to animate an image. At training time, we assume that we have a large data set composed of many videos that depict objects of the same category, like for example, people doing Tai Chi. And we will sample pairs of frames that we will refer to as source and driving. And we're going to train our framework using just a simple reconstruction loss. So it means that from the source and driving frame, we will try to reconstruct the driving frame. But we will use a very specific architecture such that we will learn a good motion representation. So how does it work? We have a network that is in charge of encoding the motion between the source and the driving frame. And this motion representation is given to a generation network that receives as input the source frame. And in this way, by describing the difference between source and driving, the generation network can reconstruct the driving. Okay. But what is important here is to learn a good motion representation in such a way that the information, the appearance in the driving frame is not leaking through the motion representation. I will come back to this in the next slide. But once we have this framework, how do we do at test time? So at test time, we hack the system and we will change the input of the motion network. So what we do is, if we have a source image, we take the frame 0 and frame t of the driving image, of the driving video, sorry. And if we assume that the initial frame 0 is aligned with the source image, what we can do is to estimate the motion between frame 0 and frame t. And in this way, the generation network will generate an image with the appearance of the source, but as after the motion corresponding to the frame pairs 0 and t, right? So you're going to get an image of the person in the source image, but as it is after moving, as in the driving video, between frame 0 and frame t. Okay. And then the next question is, what is a good motion representation? What is a good architecture in order to have a transfer that is realistic and that transfer well between different people or different objects? And to implement this motion representation, we propose to use self-supervised keypoints. So these keypoints are keypoints very similar to widely used facial landmark or body landmarks, except that they are purely self-supervisedly learned. So we can have a keypoint detector that's gonna output confidence map for location of keypoints. We can then extract the 2D location of different keypoints, and the location of these keypoints will be driven only by the reconstruction law that we have on the output of the network. So the network, the keypoint detector, is very free to output any keypoint, but what matters is that these keypoints should be helpful for the generator network in order to be able to reconstruct the driving frame from the source image. Okay, so naturally, what's happened is that these keypoints will be, what will happen is that the keypoint detector will tend to predict keypoints that are located on the body parts that move. And in this way, the generation network has information about the body part that move a lot. And so if the network has this information, it's capable to obtain a low reconstruction loss in the output of the network. All right. So you can implement it in this way, but usually you're going to see that it doesn't work very well. What you need to add a third component, a third network, to get good images. Why so? If we look at this generation network, basically it's an architecture very similar to UNet architecture. But what is very peculiar to this problem is that if we look at the input and output, the images are not aligned, in the sense that if you look at this position, if you look at my cursor on the source image, you won't get any object at the corresponding location in the output, right? And this is very different from most image-to-image translation tasks, right? Because, for example, if you are working on colorization or generating an image from the contour, or most of these applications that are really successful in image-to-image translation, the input and the output are pixel-to-pixel aligned. And here, this is not the case because the pose of the person or the object is moving in between the two frames. And so what we need to include is a way to align the feature representation of the source image in order to provide to the decoder of the generation network a feature representation that is aligned pixel to pixel with what the network is supposed to generate. And so to do this, we train a third network. Everything is jointly trained, but we include a third network that takes as input the source image, the displacement of the key point between the two frames, and predict a dense motion representation as a form of an optical flow. And this optical flow can be used in the bottleneck of the generation network in order to warp the features to get features aligned with the output of the network. All right. So in short, this network is meant to go from a sparse representation that is very convenient for transferring motion to something that is to a dense representation of motion that is not good for transferring from one face, one person to another, but that is very good to help having good reconstruction in the generation network. Okay. And we get some first result with these methods, but then we realize that there are some weaknesses. The first one is that if you just encode motion with a displacement of 2D keypoints, there are some types of motion that you cannot encode. For example, if a person is rotating the arm, this you won't be able to encode it with 2D keypoints. And so to address this issue, we ask the keypoint detector to predict not only confidence map for every keypoint, but also coefficients of the Jacobian matrix corresponding to the affine transformation in the neighborhood of each keypoint. And so in this way, we can describe motion that are significantly more complex and that cannot be described with just simple keypoint shifts. And the second contribution that we add in this second work was that in some part of the image that we generate, some regions cannot be obtained by simply warping the features of the initial image. Indeed, if you look at, for example, this part in the image, since here we don't see the background because there is this occlusion due to the arm of the person, when you generate the output image, you need to impaint what is in this region. And so you should not use the features that come from the source image in this region to predict this part of the image. You should use the neighboring pixels. And so to avoid that the network uses these pixels that correspond to the arm and not what is occluded by the arm, we just ask the dense motion network to also predict an occlusion mask that can be used just to mask out features that should not be used by the decoder to reconstruct the frame. Okay. And so before coming to the results, I just wanted to step back and discuss a bit the main difference with another method that came at the almost same time as our approach. But what is interesting in this work is that their approach is that they use supervised keypoints. First, so the first limitation is that you can apply it only on faces and full body, for example. And the second major difference is that they learn a generator, encoder-decoder, that go from the landmark to the output frame. And this makes sense because the landmarks of the target pose are aligned with the image that you want to generate. But the main difficulty by doing so is that you need to encode the whole appearance of the image of the person into a single embedding that you will provide all along the generator network. Instead, what we do in our approach, we keep all the appearance information of the source image, and what is given to the encoder is the appearance, and we warp based on the key point. Why they do the opposite? They give the key points and try to provide the appearance information. And so I think this is a key difference that makes a lot of difference in terms of performance. It's better to encode appearance, keep the information, the spatial information of the appearance, warp it thanks to a motion description, rather than trying to encode the whole appearance of the person into a single vector and losing completely the spatial dimension of the representation. So let's see some videos. So this is what we get by training on the voxelab dataset. So we get different images that are people that do not appear in the training set. And we see that we are still capable of generating realistic motion with a video that was not present in the initial dataset. But the good point of our method is that if we have a large data set of cartoon videos, then we can also do transfer on that kind of data without any prior information. So it gives you an idea what we can do with this. But before moving on to the next part of the talk, I just wanted to give also a kind of idea of what could be the possible application of that kind of methods. The point is not only to generate nice videos of people talking, but I think there are much broader possibilities of applications. One of them is video conferencing. So we published 2 years ago a paper where we show how we can use that kind of approach for video conferencing. So we are in applications such as Zoom. And the main advantage of our approach is that if we have a source image of one of the person that is on the Zoom, what we need to transmit to represent and to be able to reconstruct a future frame is just the displacement of these key points, right? We can also transmit the affine transformation, but basically just transmitting the key points is an efficient way to encode the video. And so this is how we came with a video codec designed for video conferencing, where basically when we receive an input video, we can just use any image codec, image compression framework. We transmit it. And then for every frame, we can use our key point detector trained in a self-supervised way. And we just encode the key points. We use entropy coding to get higher compression gain. And then we can use our generation network and our dense motion estimation network on the decoder side to just reconstruct the driving frame. So we can just take the model that we previously trained in the previous work, and just by splitting which part is on the encoder side, which part is on the decoder side, we can end up with a video codec. And so we managed to show that with this kind of approach, we can outperform existing general purpose video codec, such as HEVC or VVC, for example. So that's it for the first part of my talk. And so now I'm going to focus on the second task, that is do as I say. So in the do as I say, again, we have a large data set that is unlabeled, no annotation. And here we will assume that this video depict an object moving in an environment. So for example, it's a tennis player that is moving on a tennis field. So for now, we assume that we have just a single object moving, right? We don't have two players, but we will come back to this later. And what we want to do in this task is to use this unlabeled data set to train a neural network in such a way that at test time, the user can provide some discrete actions that will be an input to this network in order to control what's happening in the generated video. So for example, if we start from this video frame, the user can choose one of the actions to tell the player to move right, another action to stay, one to move forward, and one to move right, for example. Okay. And again, we want to do this without supervision and without using too much prior information on the type of scene that we are dealing with. So how do we proceed? Actually, we're going to adopt a framework of procedures that is very similar to what we were doing before. We need to learn a motion representation in a self-supervised way with, again, an encoder, a decoder. We have a reconstruction loss, and we design our architecture in order to have a good motion representation that correspond to what we want. So now we assume that we have frame pairs, two consecutive frames, t and t+1. And in our encoder, we will encode independently each frame to get some features that represent each frame. We get features ft and ft+1. And the goal is to get a discrete label, AT, that encodes the difference between FT and FT plus 1 in such a way that our decoder network is capable to reconstruct the frame T plus 1 using only the features from the frame FT, right? So the goal is to have a representation of the action space, of the motion space, that is sufficiently clustered in discrete regions in such a way that the reconstruction loss here on the frame T is sufficiently low. Right? And so when it comes to practice, when we want to make this very simple principle to work, you need to make it, everything is a bit more complicated. So the third thing that you need to do is to make your network recurrent, because it won't be possible to generate the next frame from just the current frame. You need to know also a bit the past to get like temporally consistent frames. And so the third thing that you're going to do is to use a recurrent neural network that encodes information from the past and help at every step of the network to reconstruct the current frame. And the second thing that you need to handle to make this whole network to work is to address the problem of the stochasticity of your environment, in the sense that your environment is never deterministic. And I mean that every action can be performed in different ways, right? If you have an action moving left, for example, there are hundreds of ways to move left for a tennis player. And so if we encode the action, so the motion between two frames with just a discrete action, it's going to be really hard to get a very low reconstruction loss here on the output of the network. So we don't describe the motion only based on discrete action, but on some a representation of motion that we call VT, that is a variation of this specific action AT, and that describe what is in which manner the player move left or move right or move forward. Okay. And what is hard here is that we need to find a way that the network will use both AT and VT, because if you do it in a naive way, since VT is continuous, it can encode much more information about the temporal dynamic in between FT and FT plus 1, and the network will just forget about AT and will encode all the information in the continuous variable VT, right? So we need to find a way for the network to encode what is not discrete, that is continuous, but in a way that if you don't know AT, the meaning of VT is not enough to reconstruct the frame. So how can we do this? So to rephrase the problem, we need to avoid the leaking issue, in the sense that we should not have all the difference between FT and FT plus 1 that go through only VT. The third thing that we need to do is to project FT to get an action embedding, right? So it's just a small MLP network that just reduces the dimension of FT. And then we predict from the difference between the action embedding at time ET plus 1, we predict what is the action in between the frame T and T plus 1. And more precisely, we don't predict on the action, we estimate the probability PTK of each action. All right. And so once we know the probability of each action, what we can do is that we can compute the centroid CK of each action, right? So we compute the centroids in the space of DT, okay? And at this stage, we define VT as a weighted sum of the difference between the input DT that we estimate in the current frame pairs and the corresponding centroid of the class. So let's say, for example, that the class number K is the most probable, has the highest probability. So what this sum will be equal basically to the difference between the mean feature for the action K and the one in input, right? So basically, VT will really encode the difference, the specificity in the way the action is performed with respect to the average manner of performing the action. And in this way, the network cannot bypass AT, right? Because you need AT, the discrete action, to know which centroid to be compared with, right? And so that's it. In this way, we have solved our two problems: a recurrent neural network to handle temporal consistency, and a way to encode continuous action, continuous to have a continuous representation of motion without having this leaking issue. Now we can train our overall pipeline. How do we train it? As I said, mostly reconstruction loss, but we add additional reconstruction loss where basically we measure reconstruction in feature space that are well suited for our problem. So the first one is that we can measure this reconstruction in the space FT. So basically we check if from the reconstructed images, we obtain feature representation that are similar to the initial feature representation that we have in the first encoder, right? And then we also measure this in the action space. So basically we want to check that if we evaluate the action in between the input frame FT and T+1, if we check what is the action performed in the reconstructed video, we want to check that we still have the same reconstructed action, okay? And we have a specific way of measuring this loss. We could do it just with a simple MSE or a cross entropy loss if we are speaking about AT, but we choose to do it in a different way. We use the mutual information between the probability of the action initially detected and the one that we have in the reconstruction loss. Why do we use mutual information? This mutual information has two advantages. First, to have a high mutual information, you need to have the same action, but you need also to be sure that if you get different inputs, all the different action will be predicted, right? Because if you always predict the same action AT on all your videos and all the frame pairs, basically you don't add information when if you know PT hat, you don't know more of PT if you always predict the same PT, right? So this way of formalizing the reconstruction loss has this advantage of both enforcing reconstruction, but also diversity of the action that can be predicted by the network. Okay. And so this is the kind of video that we managed to generate. So sorry for the multiple compression that we have through YouTube plus Zoom, but I hope you can still see well enough. So we trained and tested on multiple data sets. So again, the bare data set where we control this robotic arm with some discrete action. So you may see on the top left corner, the index of the action that is chosen at every time step. We tested also on a breakout. So this is this widely known Atari game, and on the tennis data set. Okay, one more time. Sorry, it's left my full screen. Okay. Okay. And so this first work was quite interesting and novel because it was the first time that we could control like the video generation process in an interactive way with discrete actions. But this approach was still suffering of many many problems. The first one is that, for example, in the case of tennis, we could have only a single player, because otherwise you need a single discrete label to describe the motion of two different players, right? So if you do so, you won't get a very meaningful space of discrete action, and so it won't be easy for the user to really control what's happening. The second limitation that is there is no 3D mold. We just use naive CNNs, and so we cannot, for example, control the camera position, right? And also the set of like the diversity of the videos that we could generate at test time was still limited. For example, you could see that we were training on videos from Wimbledon, and so we can train only on videos of this tournament. If we want to generate Roland Garros, we need to get data and train again. And so we wanted to have more diversity, and we wanted also to see if it's possible to even control the style of what we have. So for example, we start generating a video, and then we can change the style of the player. So this is how we came to the idea that initially we wanted to do playable video generation in this task of do what I say, but we wanted to go beyond this and to really have what we call playable environments. So environments in the sense that you can really do much more. You can control the camera to generate different point of view. You can control the style of the player, of the background, and you can also control each player independently with two sets of discrete actions. All right. And so how did we do this much more advanced, how did we tackle this much more advanced problem? We adopted a very similar approach. We just needed some slightly more supervision in the sense that we used a person detector. So now we consider that we are capable in each frame to detect where is the player. So you see that with modern computer vision tools, I mean, we can reasonably assume that we can detect tennis player on the field. And so we don't rely on too strong supervision. And so then we will still use a very similar architecture where we have an encoder for each frame, a decoder to reconstruct each frame, and in between, we have an action module where we try to encode the difference between the states, the features that are estimated in the two frame IT and IT+1. But the first difference is that now we don't get only a single state, a single feature descriptor for the entire image, but we get one for each player, here in red and green, and a third one for the entire background. Okay. So in this way, since we have explicit representation for each object in the scene, each player, we can much more easily manipulate the content of the video by acting only on one player or the other one. And similarly, now we can have an action module that is specific to each player, one for each state. And the second novelty that we needed to introduce is to completely change the type of network we were using for the decoder. Before, it was just a standard convolutional neural network with upsampling layers. And now we replace this decoder using a neural rendering technique. So in particular, we use a very popular NeRF model, so neural radiance field. So I won't detail too much what is a NeRF. I guess many of you know already. But basically, if some of you don't know, it's a novel view synthesis method, where basically if you want to generate a new view for some 3D content, if you know the camera pose, you will generate the image by simply casting all the rays corresponding to all the pixels in your image. And so for every pixel, we will check all the points all over the ray, all along the ray, and we will check what is the density at this position of the 3D space. And then for each point of this 3D space, if we know the density, basically is there an object at this position or not, and if we know also the color associated to this 3D point, we can estimate what color should be put in this value at this location of the image, right? And so to estimate the density of the color in every location of this 3D space, what we do when we use NERF, we simply use a neural network, an MLP, that takes as input the 3D coordinate of the point and the direction of the ray, and we train this network in order to be capable of predicting the color and the density. And so basically we reuse exactly the same architecture. So for every point of the 3D tennis field, for example, since we were showing example with tennis, this network output density and colors. And in this way, we can output an image, but in such a way that if we change the camera position, we can also regenerate this view from a different angle. And so in this way, we can handle multiple objects and we represent everything in 3D. So this is just to illustrate what is the 3D action space that we have learned in this way. So if for this player, for example, we start from this position and we play multiple times the same action, depending on the action, we will end up right here, or we will move forward, move slightly left, have a large motion to the left, or slightly backward, and so on. And the same happens for the other player. And now we really have everything that is happening in 3D. And so I will show you some more videos to show you what we can do. So the problem of working with tennis videos is that if we want to do novel view synthesis, change the camera pose, we don't know the ground truth of what we have only a single camera available, so we cannot do this. So in all our experiments, we use this tennis dataset, but also a dataset that we collected using Minecraft, because in Minecraft, since this is a video game, you can re-render any view with exactly the same action. So in this way, we can have a quantitative evaluation of our multi-view generation. And so here, what happens is that we have a scene, and we can, for example, here, each player, if we have two players, can control the characters in the video game by choosing discrete actions. And what is really great here is that we don't use any information about the action that we can actually do when we play Minecraft, but still we are capable of learning how we could control a Minecraft character. And the same happens here for tennis. We can choose a different action to move one of the two players. But since we use a neural rendering technique, we can also manipulate the camera pose. So for example, during a match, we can, while we are playing with the player, we can move the camera. We can also do it with a real video. So it means that if you have your favorite match and you want to re-render your match from a different point of view, you can do it. And finally, we use a slightly modified version of a NERF that also receives as input a style description of our player and of our tennis field. So for example, what we can do, if we receive a video with a specific content, so for example, here a player moving forward, then even if it's in Melbourne, then we can transfer it with different styles. So this is again Melbourne, but at different time of the day. And so here, for example, in this video, we get the content of the video on the left, but the style of stylizing a video, the one in the top row. And then we can show also examples where basically here we take other styles coming from other tournaments. All right. And so we can do all this at the same time. Okay. So as a conclusion for my talk, so I hope that with this talk I managed to convince you that by just playing with the architecture and in formulating the problem as a self-supervised learning problem, we can actually design new way to control the generation process. And it comes almost for free. We don't need strong supervision to get to obtain an interactivity in a deep generative model. And so I've shown it with two applications, two tasks, do as I do as I say, but we can actually extend it to many other tasks. So I mentioned this Go where I click, but I'm sure that there are hundreds of other ways to control, to provide interactivity with the generation process. And so there is still a lot of work to do in this direction. I want to say also that all the code of the methods that I mentioned are publicly available. They are on GitHub. You also have Collab to try it quickly. So you can even upload your own picture and try to animate it. And yeah, as future works, of course, we can investigate other ways to interact with the video that we generate. But I think also we can maybe try to include more advanced rendering methods to get even higher quality. And I think that many of you heard about diffusion models. And so far presented methods only based on reconstruction and adversarial losses. But I'm sure that the emergence of diffusion models will bring higher quality, maybe either better dynamics in the videos. And so I'm really curious to see what we will be able to do in the next years with diffusion models. Thank you very much.